So we have an example of a state of stress on something that's called a plane stress condition. And so what that means is that face that we're looking at right there has zero stress on it. So this is a two-dimensional problem. You see you've got X and Y labeled. So in a plane stress problem, where Z is the axis that would be perpendicular to that face, sigma ZZ is equal to 0. And these, by a plane stress problem, we can put a strain gauge on that free surface and take a reading. So you see a strain gauge is located right at that point, and it's going to be in the X direction, and it has a certain reading, 100 microns. And so what we're asked to do is solve for the unknown normal stress labeled as sigma. We're also given some material properties, modulus elasticity and the shear modulus, both in gigapascals. So we have three Hooke's law equations, 3D. We're going to use the one in the X direction because that's where the gauge is oriented. So epsilon XX relates to the three normal stresses. Sigma ZZ is equal to 0. So we're going to manipulate this just a little bit. We want to solve for sigma, which that sigma would be that. So we're going to rearrange the equation. Let's go ahead and take this to the other side right there, flip it all around, multiply through by E, and we would end up with an expression for sigma XX, which is sigma in the picture. So as we look at this equation, let's lay out what we know, and perhaps there may be something else that we need. So clearly that's what we want to solve for. We know epsilon XX, that's from the gauge reading. We know E, which was given to us. I'm going to take that down to megapascals. Sigma XX is sigma, and sigma YY is -10. So again, numbers-wise, we've got up here 10 in compression, and so compression is expressed negative in our equations. So the only thing we don't have is Poisson's ratio. It wasn't given to us, but we do have E and G, and we remember that there is a relationship between E, G, and Poisson's ratio. So all we're going to do is just flip this thing around a little bit because we know this, we know that, that's what we want. So let's just play around with the equation. We can go ahead and turn it all over, bring this to the other side, divide by 2. So this to the other side, divide by 2, divide by G. And we've got an expression pretty close, so Poisson's ratio is equal to E over 2G minus 1. We'll plug in what we have for all those values. So 200 for E. G was 75. That was all in gigapascals, so units are consistent. We've got a 2, subtract 1, and so we've got a value for Poisson's ratio of 0.333. So we've got everything that we need. We can go ahead and finish up the problem. We'll just go back to the equation for sigma XX. Just write that again. So now everything is known. So we'll just go ahead and put all those numbers in. Known, 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 and known. So our numbers look like epsilon x was 100 times 10 to the minus 6. E, we're going to use 200,000 megapascals plus 0.333 times sigma y, which was minus 10 megapascals. So our units are consistent. Go ahead and multiply all that out, and we would end up finding that sigma XX was 6.7 megapascals. So it's in the direction drawn if we go back up here. So that would mean that our actual state of stress looks like 10, 16.7.